All right, work another problem here for you. So I have a mom here pulling her daughter, 21 kilogram daughter, in a 13 kilogram sled along a walk that's 2 kilometers long there. So out for a little walk one winter day. The coefficient of friction between snow and the sled is 0.12. The sled moves at constant velocity, so no acceleration. How much energy does mom expend on the walk pulling her daughter? So whenever you read this, how much energy does mom expend going some displacement, a walk pulling her daughter? Remember the definition from the last video of work is the amount of energy that you expend displacing an object, or the amount of energy you expend applying a force to make an object move, some displacement there. So we're solving for work. Work equals force that the mom applies, or force of pull, delta x, which is going to be 2 kilometers. Careful, your mind should be saying convert there. Cosine theta. Now, this is set up with no angle, right? So cosine of 0 is 1, meaning that this entire term, cosine theta, just goes away, leaving me with work equals force times delta x. Now, I've already drawn a little free body diagram over here. I've got force of pull going to the right, normal force going up, force of gravity going down, force of friction opposing it. The reason we're going to need that, let's just go ahead and let's start plugging things into our work equation. Work equals Fp, which we were not told in the problem, times delta x. Now delta x we were told 2,000 meters. That's what 2 kilometers is converted back to base units, meters, right? So I need to figure out what force of pull is. Well, so let's come over here to my free body diagram, and let's just go ahead and start solving Newton's second law stuff. So I've got in the x-axis, sum of the forces equals ma, and I'm going to call to the right positive and to the left negative here. So this is going to be Fp minus Ff equals ma, but I know a here is 0 because we're moving at constant velocity. So that's going to leave me Fp minus Ff equals a goose egg. So Fp must equal whatever the force of friction is. Now force of friction can always be broken down, right, into mu, let's get a good kind of front tail on that, mu times normal force, Fn, and I know what mu is. That leaves me just wondering what normal force is. So Fp is going to equal, let's see, 0.12 times normal force. And if I can figure out normal force, I got force of pull, and if I got force of pull, I've got my work. So now let's come to the y-axis, right? In the y-axis, sum of the forces equals ma. I've got normal force going up and gravity going down. I'll call up positive, down negative. So Fn minus Fg equals, and I'm going to go ahead and tell you, acceleration is 0, right? Because the sled isn't flying up into outer space or plunging down to the depths of the earth. So that leaves me with kind of what you're used to. Force of gravity is equal to normal force. So my normal force comes out to equaling mg. So whenever I multiply the mass of 34, which comes from adding the child's mass, the daughters, and the sleds together, times 9.81, I come out with my normal force equal to 333.54 newtons, right? And that's going to now get substituted in over here. So let me grab a little bit more workspace down or over here. So Fp is equal to my mu, which is 0.12, times my normal force, which I just found out was 333.54. So you plug that into a calculator, and you come out with 40.02 newtons. All right, so now that can be substituted up here, right? So, 40.02 times 2,000 ends up giving me 80,000 joules of work. 80,000 joules and 2 sig figs, so I need a bar over that 0 there. One last thing for this lesson here. I want to actually show work going straight up is the same as work going along a ramp. Now, a ramp is a type of simple machine. I'm not planning on teaching simple machines with mechanical advantage. Reason for that is all of the simple machines, everything can be done with just simple physics, the work equation there, and that's a better way to tackle it in the first place, in my personal opinion. But anyway, I have here a ramp that is 1.2 meters long and 0.94 meters high, and we're going to push a 13 kilogram box up it. We're going to make this ramp frictionless. Now that is critical. It needs to be frictionless for this to work. Okay, so we're going to push this box up. Now I went ahead and did a free body diagram of this, FP going up, right, FG sine theta going down this way, right, FG cosine theta going into the ramp, and normal force going up directly up perpendicular from the ramp. Remember we tilted our axis. Remember all that from Newton's second law there. Now, what I want to compare is what if we just lifted the box straight up? You know, we just took the box and we lifted it up 0.94 meters. So that's force of lift times delta y, right? Work to lift it straight up, force lift times delta y. Well, this is going to be very, very easy here. If you look back at the first slide, we found that the force needed to lift is going to be the same as the force of gravity, right? Times my delta y, which is 0.94. If I was going to lift it straight up, and forget the ramp, I'm just going to take it up to 0.94. That's work equals mg 0.94. Work equals 13, 9.81, 0.94, and that gives me 119.8 joules, or with sig figs, right, 120 joules, it looks like over here in the picture. I gave you 2 sig figs. All right, so that's if we were to lift it straight up. Now, I want to do the exact same thing, except I want to go up the length of the ramp here. Now, to go up the length of the ramp, my delta x, if you will, is going along the ramp. So it's going to be 1.2 meters. So let's change colors here. Work going up the ramp is going to be force of push up the ramp, the actual force you would be pushing with on the ramp, times, if you will, what we have labeled delta x there, the length of the ramp. So work is going to equal whatever this FP times 1.2 meters is. And you go, well, what is FP here? Okay, so the only way to get that is to go back to Newton's second law and to do a free body diagram. Tilted the axis, right, all the things we've already talked about. This is happening in the x-axis. In the x-axis, sum of my forces equals MA, so I'm going to have FP minus, remember down the ramp is FG sine theta, and assuming I'm moving at constant velocity, that's the assumption I'm making for both of these, right, equals 0. So that means FP equals FG sine theta, and so FP equals MG sine theta. Okay, so now let's substitute that in there. All right, now it's just algebra. Let's plug in our numbers. So I'm going to do that here for you. And whenever you go through plugging in your numbers, you notice, uh-oh, I'm missing something. I'm missing theta. That was not given. On these type of problems, lots of times I'll give you, or you'll be given 2 things, but not necessarily another that you can quickly find, right? I can find out what that angle is. I have a hypotenuse. I have a height. I want to know theta. Well, here I know sine theta equals my opposite over my hypotenuse, right? So theta is going to equal sine inverse of whatever my opposite is, which is 0.94, divided by my hypotenuse, which is 1.2. And I come out with 51.57 degrees. Now I substitute that in, and then I have all the numbers that I need. I can just shove into the calculator. And I end up coming out with 119.8, again, 119.9 with sig figs, 120 joules. So now here's what I need you to see, right? Without friction, now that is critical. Friction steals energy. That's what friction does. It takes energy and it throws it away into heat. Okay, so we'll have to account for that in future problems. But without friction, Okay, the amount of work you do, whether you're going straight up or you're going along the length of the ramp, does not matter. You come out with the same one. In fact, ramps, all simple machines revolve around this trade-off. This is why we like simple machines. We are willing to go an extra distance, delta y, aka go a longer distance up a length of the ramp. So we increase how far we go, and the trade-off is the amount of force I have to apply goes down. Think about a screw and a nail. That's another simple machine, a screw. It's a lot shorter distance just to take a hammer and knock the nail in. The nail goes straight in, much shorter distance, right? But it requires a lot bigger force. That's why you require the hammer to do it. You can't use your hand. It's not small amounts of force. Screw, on the other hand, you're turning and turning and turning and turning for a good while. It goes a long distance, but it doesn't require much force. A screwdriver with a little bit of turning action can put a screw in. So you go a further distance, less force. That's the point of simple machines here. The point behind this problem, whether you go straight up or you go up the length of the ramp, it does not matter. The work is the same if there is no friction.